Hey there, mechanics students! I just want to remind you that throughout the year, you do a lot of homework, you do a lot of classwork, you really work out your mind, but you can't forget to work out your body too. So I've got the best workout for you today. Alright, I'll catch you at the next break.
Alright, so let's go see what we got in store for our workout today. On our set list is going to be to develop Euler-Bernoulli Beam Theory for bending stress and deflections, and to solve for bending stress in beams. Super. Alright, well, if we're going to do some Euler-Bernoulli Beam Theory, we got to set up some basic rules here, and we're going to make a few assumptions to make things a little bit easier. Alright, so we're going to consider a general beam with some crazy loads on it. Very, very generalized stuff. To make it a little easier, our assumptions, we're going to assume 5 different things. The first is that the neutral axis remains the same length. Okay? And we're going to talk a little bit more in detail about what these assumptions are, but just go ahead and get them down on your paper now. Number 2, we say plane sections remain plane. Oh, that's so great. It's like the best thing. It's almost like a plank, right? Plane sections remain plane. You just plank sections remains plank. It's got to be similar. 3, small deflections, right? So we're going to have small deformations in all of these things. And basically that's an order to 2 orders of magnitude smaller than the length of the beam. Number 4, we're going to assume linear elastic behavior. We're going to make sure that we're not into the inelastic part of the stress-strain curve. We're going to stay where stress is directly proportional to strain. And the final assumption, number 5, is that we're going to use a homogeneous material. This is going to be very applicable for all kinds of metals. You know, we do steel, aluminum, brass, copper. All kinds of metals fall into this homogeneous material behavior. So hope you're ready to get started. Let's take a look at more about these assumptions.
Okay. Oh, hey there. It's important as you work out, you gotta stay hydrated too. So I hope you guys do that no matter if you're working your mind or you're working your body. Alright, so we just saw a bunch of assumptions and I just want to break those things down. So our first assumption, right, was that the neutral axis remains the same length. What does that mean? Well, we take this beam here, right? And as I bend this beam, right, the top goes into compression, bottom goes into tension. But some point between there, it makes sense that some point between the compression and the tension, basically nothing's happening. And that's what we call the neutral axis. So right here in the middle on this particular beam, the neutral axis is one length at the beginning, and after we bend it, it has no tension or compression. The neutral axis remains the same length. Assumption number 2 is that plane section remains plane. Oh, it's so fun to say that. Plane sections remain plane. What does that even mean though? Right, so I got this beam, and we got these planar sections drawn on the beam. And I go to bend it, right? After I bend it, those planar sections are still a planar section. Yeah, sure, they're rotated a little bit, but that's what we mean by plane sections remain plane. Number 3 is that we're going to do small deflections. Now that's pretty straightforward. Basically, we're saying that deflections are, 2 orders of magnitude smaller than the length of the beam. So, right, this length of this beam is what, maybe 24 inches or something? So we're talking about deflections on the order of like a ½ inch or something like that. Makes sense for most engineering applications. Finally, assumptions 4 and 5, we have our good friend Stelio. He's going to be happy. We're going to remain linear elastic, so he's not going to break. He's not even going to permanently deform. And then we got assumption number 5, homogeneous materials, something like steel, aluminum, brass, all of these things, all of these metals and engineering applications are homogeneous, right? So those are our 5 assumptions. So now we're going to get to working, doing the hard part of the workout, which is our Euler-Bernoulli Beam Theory.
All right, so this is the heavy portion of our workout today, but you got to stick with me if you're going to get them gains. If you're going to skip ahead and skip leg day, you just go ahead and take a look at equation 2 and equation 5, and then the general equation for the differential equation for deflection. Those are what we're going to need. But I hope you're sticking with me. If you're going to stick with me, we're going to dive right in. Here we go. We need to set up some ground rules. We're going to look at that beam above with the generalized load condition, and we're going to pull out dx element. It's going to bend something like this below. I've indicated the origin or the center of curvature for this beam. Here we have the neutral axis, right? So along the neutral axis, I'm going to just put points A and B. If we look on the compression face of this beam, I'm going to label 2 more points, A prime and B prime. So this is going to help us set up, how do we get the relationship between A prime and B prime compared to A and B. This is going to set up a strain relationship. All right, I just want to work with this diagram a little bit longer, so I'm going to indicate a few more values. This segment dx goes through some angle of curvature. That's going to be called d theta. I will put that d theta on both sides, so that's going to be d theta over 2 on the right-hand side, d theta over 2 on the left-hand side. Now, this assumes, that both sides deform the same. It doesn't really matter. It's going to make our derivation a little easier. But even if they don't, if you have 3/4 of the angle on one side and 1/4 on the left, it still adds up to d theta. Next, we're going to look at the arc length. I've drawn the arc length in green there. That's going to be ds. ds will be the arc length for this little segment. All right, so I told you we want to set up a strain relationship. So first, let's look at the deflection in the top fiber. I'm going to call this deflection in the top fiber d delta. If we reference the picture on the previous page, d delta is going to be the difference between A prime and B prime compared to the length of AB, right? So AB is our undeformed length at the neutral axis, and A prime, B prime is the deformed length along the compression face. This will give us a negative number, again, negative meaning compression. All right, so if we go back to that previous page so we can see what we're talking about, this distance here is going to be part of that d delta, and I'm going to say it's going to be d delta over 2 in this case, and then we have another d delta over 2 on the left-hand side, and that will give us the total d delta. Now I can relate d delta over 2 to d theta over 2 by saying d delta over 2 is equal to y, the distance from the neutral axis, times d theta over 2. If I do that, I can come up with another expression for d delta. D delta is going to be 2y d theta over 2, or just y d theta. Now in that process, I have to make sure I keep around this negative sign that means it's in compression. And so I'm going to put that sign in front here, and I'll give you a little note there so that you kind of remember that later on. You can remember that that negative is there basically just to mean that this is in compression. All right, so next we move on to our strain relationship. We always say strain is the change in length over the initial length. In this case, it's that change in the top fiber, d delta, over our initial length, which was dx. But one of our assumptions was that we had small deformations, and if we have small deformations, then dx is approximately equal to ds. So that means the horizontal x differential element is roughly equal to the arc length. Okay, that's what we mean by small deflections. So we'll now say that d delta over dx is roughly equal to d delta over ds. I have an expression for d delta above. We said that that was minus y d theta. And I got it in the wrong color ink, so I'm going to make a quick change. There we go. Now I need to come up with an expression for ds. ds, if we look at the previous, is just arc length. Arc length from circles, if we go back to geometry, arc length is always the radius times the angle. So I'm going to use the radius of curvature, that capital R, and multiply it by d theta, the angle through which it goes, that element, the arc length goes through. D thetas will cancel, so now we get minus y over r, and this is kind of our first big relationship. We can then use our linear elastic stress strain behavior to say that sigma is equal to Young's modulus, capital E, times y over r. We'll carry along that negative sign. Whew. All right. First set down, got to do the next one. Now we have to dive into cross-sectional behavior. So, in our cross-section behavior, we have a moment acting on the cross-section. I'm going to represent it like this. It's basically compressing the top and pulling tension on the bottom. So we get some sort of compression on the top. I'm going to say that this is our stress, sigma compression, or sigma C. And then on the bottom, I get some sort of tension. So this will be sigma T. This is going to be my tensile stress. All right, if I look at equation 1, the stress is related to just y, the distance from the neutral axis. And so that sets up a linear relationship. It basically says stress is linearly related to the distance from the neutral axis. And so if that's linear, that linear relationship is true, then my stress profile will also be linear. Because at the neutral axis I can't have stress, it must pass through 0 there. And I get this value. Hopefully you can make it a pretty straight line in your notes. I like to show kind of the forces from the stress acting, the stress acting on the cross-section. So that's what these arrows are going to represent, that we're like basically pushing on that block at the bottom and we're pulling on that cross-section, we're pushing it on the cross-section at the top and we're pulling on it at the bottom of the cross-section. All right, if I want to calculate what this moment is, I'm going to sum my moments about the neutral axis. My moment is always a force times a distance, right? So if I have stress, I can get to force. Stress is always sigma times area. Now, if for each little point in the cross-section, if I do sigma times dA, that's going to give me my force at some distance y from the neutral axis. Then I'm going to take my force and I'm going to multiply it by y so that I take force times distance to get moment. I need to do this at all points in the area, so I'll take the integral over the area to sum all those up across the cross-section. All right, now if I was good at math, I would just go ahead and do this. I'd knock it out. But sometimes area integrals get a little tricky, especially for a weird cross-section. So I'm going to do this derivation a little bit more simply. And I'm going to use similar triangles basically to relate kind of the sigma dA value, the sigma value, and kind of get it to be a constant. So if I consider some random arbitrary stress in my cross-section, sigma x, at any point, because I know they're linear related, I can say sigma x over the distance y from the neutral axis has to be equal to, and in this case I'll use sigma c at the top of the cross-section, over the entire distance from the neutral axis to the top. That's distance I'm going to call c. Remember when we did torsion, we said c was the distance to the extreme fiber. When we do bending stresses, we use the same c to describe the distance to the extreme fiber. If I do that, I can rewrite sigma x as being sigma c times y over c. All right, so I'm going to use that, and I'm going to put that all into this moment equation again. So now I have the integral of the area of negative sigma c y over c dA times y. Now, sigma c isn't changing in the area. It's always the same. And c, the distance to the extreme fiber, is not changing. So I'll pull those out of my integral. The only thing that is changing is y. Now, you see here we got the integral over the area of y squared dA. Y'all remember what that is from statics? I hope you do. It is the moment of inertia. So we got our moment. moment is going to be negative sigma c times the moment of inertia, which we give the variable capital I, divided by c. And now that I have this, I'm going to just generalize it back to the moment at any point in the cross-section. The moment at any point in the cross-section is just going to be whatever that sigma x was. And if I rewrite it in terms of sigma, I can say that sigma basically equals m times y over I. So instead of looking at just the extreme fiber location, this is going to be at any point in the cross-section a distance y from the neutral axis. Now, I also got rid of the negative sign. I like to look at this intuitively. Tension or compression, I think from my moment diagram, I can figure out where tension and where's tension, where's compression. So then I'm just going to use sigma equals my over I, and then just drop in a plus or minus at the end of my problem as appropriate for tension or compression. Okay, and so that's just my own personal preference. Some people like to keep the negative around, but me, I just like to use my moment diagram to come up with that value. All right, so that is our big bending stress formula. That's what we're going to use in the rest of this lesson. But while we're here, I want to develop the differential equation for beam bending. This is going to be important for a couple lessons from now when we talk about how do we come up with the beam deflection equation using the method of integration. So simply I'm going to start here from equation 1 and 2, and I'm going to set them equal to one another. Remember, they were both sigma. And this is EY over R equals MY over I. Again, I'm getting rid of those negative signs, keeping them cluttered to the minimum. I can rewrite this by canceling the y's and swinging e to the other side as 1 over r equals m over ei. This is what we call the curvature of the beam. Now I want to come up with a different expression for 1 over r that's unrelated to equation 3. If we just go back to geometry, 1 over r, which is the curvature of the beam, can be written as d theta over dx. I get that because if dx is roughly equal to ds for small deformations, and we said ds is equal to rd theta. So rewriting that, I can get that 1 over r is equal to d theta divided by dx. All right, now in xy coordinate system terms, I know that d theta is just dy dx. This is just the slope of a line. Dy dx, also called y prime. So if 1 over r is equal to d theta dx, that's going to be like 1 over r is equal to dy dx divided by dx. And so basically 1 over r gives us d squared y dx squared, or the second derivative of y with respect to x, or y double prime. All right, so I got equation 4 from just kind of geometry, assuming small deformations. I got equation 3 from our earlier relationships. I'm going to set those two equal to one another, and I basically get y double prime equals m over ei. So this says that the second derivative of y with respect to x equals m over ei. This is kind of a big equation. And what does y mean? Y is the deflection of the beam. So if y is the deflection of the beam in xy coordinates, y prime is the slope of the beam in xy coordinates, and then y double prime is the curvature of the beam in xy coordinates. We then said that from equation 3, y double prime equals m over EI. To generalize this further, we can take a couple more derivatives. I take the third derivative, basically dm dx over EI, assuming EI remains constant. So this now gives me y triple prime is equal to dm dx shear, right? So we learned that last class. dm dx shear is the same as shear. The derivative of moment equals shear. Lastly, we can take the fourth derivative of this equation, y to the fourth derivative equals dv dx over EI, which is now equal to negative omega x over EI. Hope that's helpful. Get ready for...
Glad we made it through that. Now, I'm sure you're probably tired right now. I recommend you get up and maybe do a little bit of exercises to get some blood flowing. I recommend doing some lunges. And while you're doing those lunges, maybe you want to listen to a little bit of music. My personal recommendation is going to be a song called Sexy and I Know It by LMFAO. I promise you, if you do these lunges every day, you'll be lunging your... I forget what FAO stands for. Yeah.